Hello, welcome to my channel. My name is Anch, and in this video we're going to deal with some examples of dot product of two vectors. Okay, but before we consider some examples, just very few, we really want to establish something stronger. Okay, and it's going to go this way. So let's say we have two vectors A and B. So let me put vector A and then vector B down here. Okay, such that their orthogonal projections, that's their orthogonal components, in the x, y, and z axis, okay, are a1, a2, a3, and b1, b2, b3. And if unit vectors I, j, and k are along those axes, so that we have something like this, unit vector I, j, and k, okay, these three are orthogonal components. All right. So, given those two, then we want to compute this product. That is the product of these two vectors, and it should be the dot product of these two vectors, or you can also call it the scalar product of these two vectors. Of course, now we've been able to prove a particular property on distributivity property, so we could just think about distributing. All right, just like we perform products with numbers, just normal products, and then we'll also make use of some properties of this vector product, of this scalar product, to see how that will affect us. So let me just put this down first. Okay, so these are the two properties I want you to remember. The first is that a unit vector dotted with itself will give us 1. That is, I dot I is something as j dot j, which is something as k dot k. And this is true because the dot product of a vector with itself is the square of its length. So since the length of the unit vectors is just 1, it means that all the unit vectors, their length is just 1, means that we just have one square, which is 1. Then the dot product of a unit vector with another unit vector, that is to say, where these two unit vectors are perpendicular to each other, that's what it means to be orthogonal unit vectors. Their dot product will always be 0 when they are combined. But if it is one unit vector with itself, the dot product will be 1. Okay, so using those two ideas, let's multiply these two vectors. So what I would like to do is to say this particular component multiply everything here. This second component multiply everything, just like we do normal multiplication, right? So when we have a1 dot b1, that will be a1 times b1. Then when we have the vector I dot I, that is just 1, right? So that means I will just have to multiply this with 1, which means I wouldn't change it. Now let's go on with a1 with the other two components. So with a1I dot b2j. So a1 times b2 is a1 b2. But what happens with I dot j? You could recall in this property that I dot j will give us 0, which simply means that we won't add this one. And then similarly, I dot k will be 0, so that means for the component a1i, I will only have to multiply with b1i. Okay, let's look at the second one. We have a2j. If I multiply with the unit vector, with the components pointing in the direction of the unit vector I, we'll get 0. By a similar reason, then we say a2j dot b2j, that will just be a2 times. That will just be a2 times b2, where j dot j is just simply 1. And then we look at the j dot k, it gives us 0, so we wouldn't bother. And then lastly, we have a3k, okay, dotted with a3k dotted with b1i. Since k dot i is 0, we won't write that. And then we move on with k and j will still give us 0, but k dot k will give us 1, which means we'll have to dot it with, or we'll have to multiply with b3. So this is the dot product. This is how we'll always compute it. So if we are given two vectors, the dot product will just be the product of the corresponding entries plus just the sum of the products of the corresponding entry. That's a1 b1 plus a2 b2 plus a3 b3. This is what we get, because the other ones will cancel out to 0, since the dot product of a vector with another vector, where those two vectors are perpendicular to each other, that dot product is always 0. So that's what we get. Okay, so using that idea, or using that fact, we will do the following example. Okay, I don't want to establish that. It's a very important result. So we'll do this. Number one is very simple. we just want to take the dot product of 2, 3 with, that's a vector containing 2, 3 in the I and j directions respectively, and then that. Okay, so recall this is just the product of the sum of the products of the corresponding entries, and also remember that dot product or a scalar product gives us number, so we won't get a vector as a result, we get a number. So in this case we would simply just have 2 times 1. All right, so let me just put it out here, 2 times 1, and then we add that with, we say 3 times -5, so that is 3 times -5. Okay, so we easily see what that will give us, this -5. So this just gives us 2 times 1 is 2, then this is -15, which that gives us -13. So that was a simple one, right? That's very easy to see. So maybe we could do with this, we could do millions of examples, countless number of examples. All right, maybe let's just do another one. So let's say we have this example, that is that. Okay, so you want to compute u.v, and then we could also verify that this will be the same thing as v.u. It's a very good routine practice, v.u. So we'll do this too. Maybe we do not know whether they are the same. We know because we dealt with that property, but we'll just do both sides. All right. Okay, so let's just question it for now. Okay, great. So what is the dot product of u and v? That will give us what? Well, from the establishment, we could say we will just have to multiply the coefficients of the unit vectors pointing in the same direction, right? Something like that. So in this case, we have 1 times -1, times -3. That will be -3. All right. We add it with. You may have to rearrange. This is -2j. Then this is -1j. We multiply those two, we get +2, and then we add it with, this is +1k times 15. That's just 15k. So if you add this up, that should give us +14. I hope that is clear enough. Okay, maybe let's do the other order. It will be easier to see, or make it easier to see. So we want to compute this vector, that is -3i minus j plus 15k. That is that product, the product of this with this vector I minus 2j plus k. Okay, great. You may want to rewrite this in this notation, -3 minus 1 and then 15. Oh, sorry. Okay, then dot it with 1, -2 and then 1. Good. So this gives us, well, we say -3 times 1, that is -3. We add it with -1 times -2, that's +2. Then we add it with 15 times 1, that is 15. So when you say -3 plus 2, that's -1, plus 15, that's +14. So this was correct. I know it may not have been really clear, but I hope this method is clear enough. So you could just do the same thing for that. That is u.v. The results are exactly the same, of course. That's what we always expect. So you could go there, look for examples, and then take the dot product of those two vectors, and the result will just be a simple number. All right, I hope you enjoyed the video. Please don't forget to subscribe to my channel, share the video with your friends. It's a way to encourage me to make videos like this. And of course, if you subscribe to my channel, I'm really, really grateful. Thanks for watching. We'll continue from our next video.